The goals of this chapter involving reaction rates are: understand the concept of rate constant K. This is lowercase k, not uppercase K. Be able to formulate the rate expression for a chemical reaction. The rate expression is different than rate law. Be able to write a rate law for any type of reaction. So again, that's very different than the rate expression, so be able to discriminate between the two. Be able to understand what is zero order decay, first order decay, and second order decay, and make sure you do problems involving them. The equations for each type of decay, zero, first, and second order, will be given to you, so you do not need to memorize them. Be able to understand Arrhenius Equation. This chapter notes has a problem involving the Arrhenius Equation. And finally, understand what a catalyst does to a reaction coordinate diagram and what a catalyst does specifically to your rate constant K. So basically, the idea of chemical kinetics or thermodynamics is, does a reaction take place? Another word for kinetics is rate. Now, thermodynamics deals with the heat aspect of whether a reaction is going to go or not, endothermic versus exothermic. And kinetics really has to do with how fast. So we're dealing with rates, we're dealing with speeds, and we're dealing with velocities of a particular chemical reaction. So how fast does a reaction proceed is kinetics. And the important thing is that we measure reaction rate, or the speed of the reaction, not in, like a car would be miles per hour, or a jet would be, several thousand miles per hour, or human would be footsteps per hour, a human walking. We denote reaction rate by concentration over time, and usually concentration is given in molarity. Now remember, big M is moles per liter, moles per liter. And how much of that reaction, that concentration, dwindles over time. So if this is a reactant, it's going to dwindle over time. If it's a product, it's going to increase over time. So the reaction rate really is, for a reactant, the negative concentration over time, so negative molarity over seconds, and product, because we expect it to increase over time, would be a positive value of molarity over second. But this is a rate, okay, something miles per hour, meters per second, footsteps per hour. It's a concentration per second because we're dealing with chemical reactions, and those are the type of units you should familiarize yourself with, molar per second. So for a typical reaction, A goes to B. Remember, A is the reactant, B is the product. We expect A to decrease, and simultaneously to A decreasing, B, the product, will increase. So the rate of change in concentration of A over time, remember delta is change in concentration of A reactant over some time increment. So it could be, remember, time is final minus initial, so some increment of time that we're measuring the reaction rate. It could be a very long time between we measure the concentration of A, it could be a very short time between measurements of the concentration of A. So that's where the time comes in. Now this lowercase t is time, it's not temperature. Temperature is usually capital T. And so change in concentration of A over some time period T, delta T, and while this reactant is decreasing negative, the product B is going to increase in time, so we have a positive sign. And it really depends, again, like before, how many times we sample the reaction. Are we going to measure B over a long period of time, or are we going to measure B over every second, or every 2 seconds, or every millisecond? So that gives us the rate. Again, change in concentration of B over time. These two are rates, and the concentration units, the units are going to be molarity over second. Concentration, molarity, time in seconds. All right, so again, don't forget, because the concentration of A, the reactant, decreases with time, A is negative. So coming back to A going to B, here's a particular reaction that we can measure over time. And as you can see here, we have the reactants in the black circles. And then generally, that's A. Generally over time, as the clock ticks around, we get more product B. So you notice B is increasing, and A, which is the black one, decreases. So as we said before, the rate of A goes down because it's a reactant, and the rate of B, its concentration over time, is going to go up. and that's what's shown here. So notice our units here, time is seconds, so, or it could be minutes, it could be hours if it's a particularly slow reaction. If it's a very fast reaction, it could be in nanoseconds or picoseconds or milliseconds, and number of molecules. Some measurement of the chemical, okay, whether it's product or reactants. And this is what we would expect, okay? And now when we introduce this delta T term here, we're introducing time, and time really tells us how fast the reaction is going to proceed. Here's an actual reaction. If you take liquid bromine, the diatomic liquid, and react it with formic acid, you're going to get bromide ion, some H+, which is a proton, and carbon dioxide will evolve. So this actually has a brownish red color. And over time, you can see here, as you add the formic acid, the acid is actually going to break down the bromine diatomic into the ion, and now you have something that's colorless. So what time scale does this occur? Does this occur in a matter of hours? Does this occur in a matter of days? Does this occur in a matter of seconds? Does this occur very, very fast? So you're going to need, something that occurs in milliseconds or picoseconds. So that's how that's the focus of this chapter. And usually how we would measure this, though this is not going to be tested on, is we measure the absorbance of the color. So you can see over time here, as we get time elapses, that reddish color which absorbs at 393 nanometers gives you a peak, it actually decreases. So that's how we actually measure the progress of this reaction. But this is how we do detection. The purpose of this chapter is really time. Okay, is this going fast? Is this going slow? What is the rate of bromine being decayed? What is the rate of HCOOH, formic acid, being decayed? What is the rate of this product being formed? What is the rate of this chemical product, H+ being formed? And what is the rate of CO2 gas being formed in our units of molarity over seconds? So chemical kinetics, as we stated before, has to do with how fast the reaction is going to proceed. Some reactions proceed very, very fast, maybe on the order of, some reactions occur very, very slow, maybe molarity over seconds. And then some reactions are kind of intermediate. So this concept of speed is really what we have to concern ourselves with when it comes to chemical kinetics. Now there's two things that really influence how fast the reaction is going to occur, and that is K. This is going to be a rate constant, and do not confuse lowercase k with uppercase K. Okay, lowercase k is what we're studying in this chapter, is a rate constant, and uppercase K is the equilibrium constant, which is going to be in a later chapter. So a gross definition of lowercase k is product made over time, or if you're talking about it from the reactant perspective, let's say you're a reactant, rate is how much the reactant is consumed over time to produce product. Another very, very critical point is that the units of K are going to differ. All right, so the K units will differ dependent upon whether the reactants decay in a zero order, first order, or second order. So one of the things that influence how fast the reaction occurs is the rate constant K, and then the second component is the initial concentration. So more concentration of reactant would give us more product. Less concentration of reactant that we started out with will give us less product. Touched upon before, but you got to remember this rate is going to be minus for a reactant in a generic reaction. In the products, that rate is going to be positive, and also rate is some change in concentration over time. This, for a chemical reaction, is its speed. So is it going to decrease very fast, and this will increase very fast, or this will decrease very slow, and henceforth this will increase very slow. So that is rates. All right. Typical reaction, A to B, your products are going to increase over time, your reactants are going to decrease over time, the rates of the reactants are going to decrease over time. Okay, so we measure this usually in the average rate of the reaction, and the average rate really depends on how many times you sample this. So you can measure, let's say, for example, every second, every 2 seconds, every 10 seconds. So the more you sample, more times you check, the more concentrations you get. Remember the trajectory. This should decrease. Reactants and products should increase over time. So that's how you get a average rate. The instantaneous rate is the reaction at a specific point in time. In calculus terms, this is actually the derivative. If you take the derivative of a rate, you actually get the acceleration. So the instantaneous rate is how fast the reaction is accelerating. So here's some real data between the reaction with molecular bromine and formic acid. Molecular bromine is actually reddish brown in color, and over time this Br2 is going to decrease and turn colorless. And so over time you see a very interesting thing here. The reaction rate, this K term that's going to be the focal point of this chapter, if you plot it, concentration of the reactant, you see it's linear. So the reaction is going to proceed at a certain rate, and that rate is actually constant. Right? So if you take all these rates, and you notice here that it's constant. So whether you're looking at this reaction at 50 seconds or whether you're looking at this reaction at 350 seconds, the rate is going to be roughly the same. So the rate constant is going to be the same for this particular reaction, but the order of the reactant, that will be either 0, first, or second order. So that's an important point here. So let's take a look at a reaction here. We want to discriminate the rate expression, which is basically how much a rate the reactant decreases versus how much the product increases over time. So you can see here the rate expression is just taking the stoichiometric coefficient and putting it on the denominator side. So you're going to need to balance this equation here to write the rate expression. So let's go over this here. 2 hydrogen peroxide goes to 2 water plus oxygen gas. So we have 2 H2O2s. So it's going to decay by 1/2. And don't forget the minus sign because it's a reactant, and reactants decay over time. So minus 1/2 is going to equal to, so this equality has to be maintained. So if this is going to decay by 1/2, the products are going to have to form, and it's going to have to form for 1/2 of water over time and 1 part oxygen gas over time. So basically the rate expression is that you take the stoichiometric coefficient and you put it in the denominator essentially. So, and then don't forget the products become negative because they're decaying. The reactants become positive because they're increasing. Another thing you can realize is that oxygen is a gas. So you can actually do the gas law and get the concentration here in terms of pressure, because gases, if you remember, can have a concentration, but they can also have a pressure. You can either measure it by a concentration, in this case moles, but you can also measure it as a pressure. So if you use the ideal gas law, PV equals nRT, and N is the number of moles, V is the volume. So I take N divided by V, and I take this P and divide it by RT. So V goes to this side of the equation, RT goes on the outside of the other side of the equation. So you get N over V moles of gas divided by the volume of the gas it occupies is equal to P equals the P divided by RT, gas constant times temperature. So if N is in moles and V is in liters, then you have moles per liters, which is just concentration. So the concentration of the gas is going to be P over RT. So you can plug that back into your rate expression and get a rate expression for this reaction. So the rate expression is not a rate law. That's an important point. And the rate expression is sort of an equation that equates the reactant decay over time. And how is that equated to the product increase over time? So we can also express this in terms of pressures. So it would be the decrease, or the increase of the pressure of CO2 over time. P equals RT is the same thing as concentration, plus the 2 times. So there should be a 2 here. Pressure of oxygen over RT times T, delta T, times 1/2, because you're making 2 moles of this. And that's going to equal to the pressure of CH4 minus, because this is going to decay, divided by RT times delta T. Big T is your temperature, lowercase t is your time, that's a minus. And plus another minus 1, there should be a 2 here, 1/2 of the pressure of oxygen, 2RT times the increment of time. So this equation should equal to one another. The accumulation should equal to the decay because the law of conservation of mass. So let's do a practice problem here. Suppose hydrogen gas is being formed at the rate of 0.078 molarities per second, or molar per second. At what rate is P4, this is called white phosphorus, is being formed, and what rate is pH3 being reacted? So here's our balanced chemical equation. You should have all the information needed here to write the rate expression. Remember, it's going to be the inverse of the stoichiometric coefficient, so it's very critical that you balance an equation here. All right, so let's look at our solution here. This is our rate expression. So minus 1/4 the change in concentration of pH3 over delta T equals plus the change in concentration of P4 over time plus 1/6. Okay, so that sixth goes in the denominator, and it's going to be plus 1/6 change in concentration of hydrogen, a gas, over time. So that 6 here becomes the 1/6 here. So this is concentration. All of these are gases. So you can also express this in terms of pressure. But since we're given concentrations, we'll go ahead and plug in our concentration units here. So the problem tells us that H2 is being formed at a rate of 0.078 molarity per second. But if you notice here, we got 6 moles of hydrogen gas. So we got to figure out the change in concentration of H2 over time. And in order to do that, we don't have change in concentration of H2 over time. We have change in concentration of 1/6 of H2 over time. So what we do is we actually do, because this is 1/6 of the change in concentration, to find the change in concentration of just 1 mole, we multiply this concentration by 6. This was the concentration given to us, and we get 0.468. All right, because 6 moles are being made for every 1 mole, another way of saying this is that we're getting 6 times H2O than P4. So to get P4, it's really just going to be 0.078 molarity per second. Okay, right? Because you get 6 times the amount of H2 gas for every 1 mole of P4 gas. So 6 times the molarity of, or 6 times the rate of the H2 gas is 0.468. 6 times less that you're being made of P4, remember, this is made 6 times less. So 0.468 divided by 6 will actually give you the amount of P4 being made. It's going to be 6 times less because they're in a 6-to-1 ratio. So it's going to be 0.078 molarity per second. Okay, it's important to get the unit. You got to realize that pH3 over time is decaying at a rate of 1/4 per unit time. Negative because it's a reactant, and reactants are going to decay and products are going to accumulate. So let's just make pH over time, its concentration rate, equal to x. Okay, and it's negative because it's decaying. So letting this being x, we let minus 1/4 x equals to 0.468 plus 0.078. And solving for x, we get minus 2.184 molarity per second. So this is going to decay at minus 2.2 molarity per second. This is going to increase 0.468 molarity per second. Remember, 6 times as fast. And then P4 is going to accumulate 6 times as slow, which is 0.078 molarity per second. Now, if you plug in these values to this equation here, decay is going to equal to this accumulation plus this accumulation. This, in essence, is what a rate expression is. All right, coming to one of the more important sections of this chapter is the rate law. So there are 2 things that the rate of the reaction is dependent on. It's dependent on the initial concentration, so more reactants equals more products, and it also depends upon rate constant K. So the rate law takes this generic form. So the rate law basically takes this manifestation. Rate is going to equal to some K. It's very important you recognize that K will have different units. times the initial dependent upon how the reactants decay. So K is your rate constant times the initial concentration of F2 raised to the order X. So that's what you have to find, the order of the reaction. Okay, will fluorine F2 decay with zero order kinetics? Will it decay with first order kinetics? Or will it decay with second order kinetics? Times the initial concentration of ClO2, how much of that you started out with, its concentration raised to the power of order Y. So again, will ClO2 decay with zero order kinetics, first order kinetics, or second order kinetics? So the goal of this type of problem is to actually determine rate K and then the orders X and Y. Okay, so the orders are the exponents in the chemical reaction. All right, so for this course, you just need to know that the exponents X or Y can take the form of zero order, first order, or second order. So let's do a rate law problem. First, let's go over one together, and then we'll do one as a practice problem, and then you can check my answers with yours. Before I move on, it's important to recognize that zero order has its own set of equations, or half-life, the time to decay to 1/2 its original concentration. A first order decay has its own set of equations, and it has its own half-life, which is the time again it takes to decrease to 1/2 its original concentration. And second order decay has its own half-life equation, and it has its own set of equations to determine how much a reactant decays over time. So you do not need to memorize all of these equations for whether the reaction is zero, first, or second. You can consult a rate law sheet that you can use for the exam. Right, now let's go over a particular problem here. This is rate law we're talking about. This is not rate expression. So first thing that you see when you're asked for a rate law, you notice that you're going to be given 3 different experiments. Okay, so what's the difference between experiment 1, 2, and 3? Well, experiment 1, we have 0.1 as the concentration of F2 and 0.010 as the concentration of ClO2. Always be cognizant of your units. And then you have the rate here. Notice the rate of your reaction, okay, molarity per second. Now let's look at experiment 2. So what did the authors do in experiment 2? They kept the concentration of F2 fluorine the same, but they increased the concentration of chlorine dioxide times 4, so it's 4 times. And they got this rate. Okay, what's the difference between experiment 2 and 3? Experiment 2 and 3, they doubled F2 and they decreased ClO2 by 4. Now, what's the difference between experiment 1 and 3? Experiment 1 and 3, they kept the concentration of ClO2 the same, but they doubled the concentration of fluorine gas, and that's the corresponding rate that they came from these concentration of the reactants. So now we got everything in the form of the rate law. We just need to fill in K and find the values X and Y to see the full form of the rate law with actual numbers. So let's do this problem here. So what experiments do you want to compare? That's the first step. Which experiments do you want to compare given the data table? Okay, so orders of the reaction are determined in the lab. You can't look at an equation and get the order. You have to do this type of data table and create 3 reactions or 5 reactions or whatever and vary one versus the other. That is, vary one reactant versus the other reactant. So first thing we do is compare experiment 1 and 2. So if we compare experiment 1 and 2, remember our goal is to find K and well as find the exponents order X and order Y. So let's compare experiment 1 and 2. So that's the rate law for experiment 1, and this is the rate law for experiment 2. I'll highlight that in green. So the rate for experiment 1 was 0.0012. One thing I didn't do here was put the units, but the units are m over second. The rate is m over second, and so that rate is going to equal to our rate law, K equals to the concentration of F2 at experiment 1, which if we go back up to our data table, was 0.10 mole. The concentration of ClO2 for experiment 1, if we go back up here, was 0.01. And we'll do the same thing for experiment 2. Remember, we're experimenting with experiment 1 with experiment 2. So the rate for experiment 2, when we look back up, was 4.8 times 10 to the minus 3. And rate is equal to K, so that K is there. what was the initial concentration of F2 for experiment 2? Let's go back up here and find that the initial concentration for F2 for an experiment 2 was 0.10 molar, and then the initial concentration of ClO2 for experiment 2 is 0.040. And so now we plugged everything into our rate law. We're doing a ratio of experiment 1 and 2. You notice what happens here when we compare experiment 1 and 2. Now don't cancel your you can cancel your k's, so I'll cancel the k here. What else can I cancel? I can also cancel this 0.10 to the power of x. Okay, that 0.10 to the power of order x gets canceled. So what I'm left with is 0.10 to the power of y divided by 0.04 to the power of y. That equals to the rate of 1 divided by the rate of 2. And so this is what we get out. Now I can group this whole thing under the exponent y, which is what I did here. And 0.0012 divided by 0.0048, the molarity per second cancels out, and I get 1/4 equals 1/4 to the power of y is equal to 1. So chlorine dioxide, from its perspective, it's going to be a first order decay. First order decay for chlorine dioxide. So y is equal to 1, so this exponent is equal to 1 here. So we're going to do the same thing to try to find order x, which is the exponent. So we will compare now experiment 1 and 3. So I should put my units here. Remember, rate is equal to k times concentration to the power times the concentration to the power for all the reactants that are in the equation. So rate here, I have my rate for experiment 1. I have my rate for experiment 3. Okay, I looked that up in the data table. And rate is equal to K times the initial concentration of reactant, which was F2 for experiment 1, which what we found to be 0.1. And initial concentration of chlorine dioxide for experiment 1 we found to be 0.010. And so we'll plug that back in here. We do the same thing for trial 3. I plug those in that I got from the data table. And an interesting thing happens here. We can cancel out our K's. And we can also cancel out our 0.10 to the power of y, order of y. We already figured it out that y was 1, comparing experiment 1 and 2, remember? And this is what we get. All right, so 0.0012 divided by 0.0024 is 1/2. And 0.10 divided by 0.20 to the power of x. I kind of grouped this under the exponent x. So 0.010 divided by 0.02 is 1/2. So I'm getting 1/2 to the power of equals to 1/2 to the power of x, and x is equal to 1. So with respect to fluorine, this is a first order decay as well. So plugging all those terms in, we get our rate, and it's going to be this, okay? And the overall order of the reaction is 1 + 1 is 2. All right, so this exponent is 1. You're not finished yet because you need to determine the rate. So we can pick any one of our initial rates and plug it back into the rate law now that we know our orders. The order of this is a first order decay. The order of that is a first order decay. We can plug this back into our rate law. So I decided to basically use trial 1, but you can use trial 2 or trial 3, it doesn't matter. So rate is equal to K times F2 times ClO2. Each one raised to the order. The order is 1 for each of these. So for trial 1, looking back at the table, the rate was 0.0012. K, which is what we're trying to solve for, the initial concentration of F2 was 0.1. The initial concentration of ClO2, chlorine dioxide, was 0.01. Okay, so the concentrations are in molarity, so M and M is M squared. And solving for K, it's 0.0012 M over seconds divided by 0.001 M squared. So you've got to make sure your units are correct, because remember, the units of K are going to vary from reaction to reaction. The units of K are going to vary from one reaction to the other reaction. It really depends on the order of decay for each of the individual reactants in the reaction. All right, so doing that in M over seconds divided by M squared gives us a final units of M over seconds, and 0.0012 divided by 0.001 is 1.2. So the final rate law is this, and that is the answer that we would want to give on any type of exam question. Full rate law, okay, not expression, but full rate law. The rate constant K with its right units times the concentration of the reactant raised to its order, and times the concentration of the second reactant raised to its order. There could be a third reactant raised to its order, a fourth reactant raised to its order. This only has two reactants, so this will be the rate law. And what you can do is you can plug in, this is the power of this rate law, is that you can plug in any reactant concentration between F2 and chlorine dioxide multiplied by 1.2, and you'll get how fast that reaction is occurring based upon your starting concentrations of F2 and chlorine dioxide. Rate laws are always determined experimentally. So on a problem, you want to look for a data table. Reaction order is always defined in terms of reactant concentration. So the order of decay, first order, second order, and zero order, has to do from the perspective of the reactants. And this exponent, also known as the order, is not related to the stoichiometric coefficient. Now, rate expression, yes. Okay, the stoichiometric coefficient becomes the fraction, becomes the denominator. Rate law, absolutely not. Okay, you need a data table. You notice here 2 is in the balanced chemical equation, but the order is 1. Chlorine dioxide actually decays with first order decay. Okay, here you have 2 moles that react, but ClO2 decays with first order kinetics and all of its associated equations and all of its associated half-life related to a first order. So let's do this practice problem involving determining the rate law for a particular chemical reaction. So you can expect to see something like this on an exam. Here's the reaction that you'll be given. Okay, the first thing you want to realize is that the form of the reaction is rate equals K times initial concentration raised to the power of the order X, or A or B or whatever variable you want to call it, times the initial concentration of I minus raised to its order of decay, Y or B or Z or whatever exponent letter you want to call it. The important thing to realize is that I minus, that Y is not 3. Okay, that Y is not going to be 3, and this X is not going to be 1. Okay, so the coefficients of the balanced chemical equation is irrelevant to your rate law. So that's what you want to do. First, you want to formulate the generic version of this. And then after you formulate the generic version of this, your job, given this data table of all these 3 experiments, the job is to calculate K, calculate X, which is the order of the decay for this reactant, and calculate Y, the order of the decay for I minus. So go ahead and do this problem and then see if it matches what I got. Okay, don't forget when you put K, the number for K, it must have the right units, and the units are going to vary dependent upon the orders of the individual reactant. All right, so remember our goal is to find the reaction order X and Y, those exponents, as well as the rate constant K with the correct. So I'll compare experiment 1 and 2. All right, so rate of 1 over rate 2 is equal to the initial concentrations of the reactants, each one raised to its stoichiometric power. Okay, so that is shown here. Just split this apart. Rate 1 over rate 2 is equal to the rate and concentrations of at 1 divided by the rate and concentrations at experiment 2. So let's plug in these numbers in, and doing that, plugging in those numbers, realizing that the K's and this one are going to cancel, along with this one's going to cancel as well. And then we're left with 0.034 to the power of the order Y divided by 0.017 to the power of the order Y. I plug in these rates for experiment 1 and 2, and I get this. Okay, you want to make sure your units are okay. And putting this math in, I get 2, and 0.034 divided by 0.017 is 2 to the power of Y. So I'm getting Y is equal to 1. So Y, which represents the order for I minus, that has a decay of 1. So it decays with first order kinetics, or first order decay. All right, now we got to find out X, which is the order of the decay of this ion, tetrathionate. So let's go ahead and do that. So this time I'm going to compare experiment 2 and 3. So going back up to my data table, 2 and 3 here, I noticed that the I minuses will cancel, and I'm left with the S2O8s, tetrathionate ion. So let's come back down here and comparing experiment 2 and 3, we do the rate law. This should be a 2. And so rate law for 2 divided by rate law of 3. So let's plug those values in. So rate of 2 divided by rate of 3, I got those from the data table. I'll get these concentrations for 2 and 3 from the data table. I plug those numbers in, and I notice that this is going to cancel. And then my values of k, my rate constant, will cancel as well. So I got to get that value a little bit later towards the end of this problem. So 1.1 times 10 to the minus 4 divided by 2.2 times 10 to the minus 4 is 1/2. 0.06 divided by 0.16 is 1/2 to the power of x. You kind of group it all under that exponent, and I get 1. So the tetrathionate decays first order kinetics, so it's also 1. So the rate law is going to be rate equals to k times the concentration of S2O8 minus 2 to the power of 1 times the concentration of I minus to the power of 1. You have to remember that two things influence the rate. All right, how fast the reaction is going to go. And what influences it is the rate constant K, as well as the concentration of the initial reactants and the order of their decay. Both of these reactants are going to decay with first order decay. The overall order of this reaction is 2. Getting the value of K, I'll just pick experiment 1, plug in that rate for experiment 1, plug in those concentrations for experiment 1. The order or the exponents are both 1. And I solve for K. I got to be very, very meticulous and careful about my units here. Okay, so since this is to the power of 1, and that's to the power of 1, I get 0.080 m times 0.034 m. Got that from the data table. So the final unit is going to be m squared. To get K, I'm going to divide this by both sides of the equation by 0.00272. And then just going by units, m over second divided by m squared gives me 1 over m second. Okay, so one of the molarities, m, cancel. One of the big m cancels. And doing that math, I'm getting 0.08091 over m second. Okay, 0.08091 over m second. So the final rate law is rate equals to K times the initial concentration of reactant to the power of 1 times the initial concentration of the second reactant to the power of 1. These are the units of K with the correct value and the correct order. So I used experiment 1 to get K. You can just as well use experiment 2 or experiment 3. And for experiment 2 or experiment 3, you'll plug in the rates and the concentrations for 2. For experiment 3, you'll plug in the rates and the concentrations for 3 and solve for K. I did that and I got the exact same answer. So this is the solving for K using experiment 2 values. That's what I get. And this is solving for K using experiment 3 values. And I get the same value for K there as well. So the overall order is 2, and this is my final rate law. So this is what you want to give on the exam. Finally, we're going to be talking about zero order, first order, and second order reactions and their own set of equations that each one of them encompasses. So for that, we'll use this table here. Now, you can actually use this for the exam, so you don't need to memorize it. But let's go over this. So first thing is bring this to the exam. Second thing is notice that we're talking about the reaction A going to B. Okay, we're not talking about A plus B going to C plus D. We're not talking about A plus B plus C going to D plus E plus F. We're talking about just one reactant going to one product. And if that A decays with zero order, you notice your rate is equal to K. And the concentration of A is just going to go down. All right. The integrated rate law comes from integrating this from calculus. And you will get the concentration of A at some time t is equal to the concentration of A naught, the initial concentration, minus KT. Plotting concentration over time, this will just be a straight line of a linear descent. And so if you double the concentration of A for a zero order reaction, rate stays the same. If you triple the concentration, the initial concentration of A, the rate stays the same. If you quadruple the initial concentration of A, the rate stays the same. All right, so here we have a concentration independence. So notice your rate just is equal to K. All right, usually the rate is dependent upon K as well as the initial concentration of the reactant. Well, if it's a zero order reaction, the rate just is equal to K, and it doesn't matter how much you start out with the initial reactant, the rate will still decay according to K. Right. The half-life for this reaction is the initial concentration divided by 2 times the rate constant, and the units of K is molarity over seconds. All right, half-life is basically, as the term stipulates, is a time, and it's the time when 50% of the reactant is gone. So the time it takes for 50% of something to be totally gone. Now let's compare a first-order reaction. Your rate is equal to K times the concentration of A. So here there is a concentration dependence. How much A you start out with determines how fast the reaction will proceed. So notice the concentration over time for trajectory has this curve. And if we want to linearize or do a linear transform of this curve, we actually take the natural log of the concentration over time. So taking the natural log of the concentration over time for a first-order reaction, a reaction with first-order decay, will give you a line, and the slope is minus K. So this is a linear transform going from here to here. And the rate law is this. So notice the rate law, how much decay depends on the natural log. Okay, this A naught is the initial concentration. The A is at some time t. And what happens if you double the initial concentration of A? What happens to the reaction rate? So if you double initial concentration of A, the rate doubles. If you triple the initial concentration of A, the rate triples. If you quadruple the initial concentration of A, the reaction rate quadruples. All right, so that is the unique feature of a reaction that has first-order decay. Half-life is 0.693 divided by K. That's also known as the natural log of 2 divided by K. I want to bring your attention to the fact that there is no concentration of A term here. So this half-life for a first-order decay, if a reactant is going to decay with first order, does not depend on the initial concentration. Okay, so that's a very strange and profound aspect of science. So if something is going to decay with first-order kinetics, whether you have 500 grams of it, 5 million grams of it, or 5 nanograms of it, or 5 micrograms of it, how long it takes for it to decay to 50% is still going to be natural log of 2 over K. So very, very interesting. And the units of the rate constant K is 1 over seconds for a first-order decay. Finally, if a reactant decays for second-order decay, so rate is equal to K times reactant squared, so the order 2, this is what the concentration over time looks like. Very much like a first-order reaction. So it's very hard to discriminate first-order decay versus a second-order decay when you're plotting concentration over time. However, for a second-order decay, to get it to linearize, you can just take the inverse of the concentration. So if you plot a series of concentrations, take the inverse and see how these concentrations change over time, you'll get a linear graph that looks like this. The slope is a positive K. And the rate law for this is 1 over A equals to 1 over the initial concentration plus KT. Right? So lowercase t is your time, and this A naught symbol means the initial concentration. So this is the 0, first, and second order trajectory for this reaction, and this reaction only. So what happens if you double the initial concentration of A? The reactant goes by square, so it's actually going to increase fourfold. What happens if you triple the concentration of A? The reactant will, because it increases by square, the reactant will go 9 times, or 3 squared. What happens if you quadruple the initial concentration of A? Well, if A decays by second-order decay, second-order kinetics, if you quadruple the initial concentration of A, the reaction rate will increase 16 times more. 4 squared is 16. The half-life for a reaction that undergoes second-order decay is 1 over K times the initial concentration of A. And then the units. Units are going to be different. So this K units are going to be different. 1 over ms versus 1 over s versus m over s. Okay. Right, let's do a practice problem here. The reaction is a generic reaction. 2A goes to B is first order. Okay, so that's a big term there. First order with respect to A. It has a rate constant of 2.8 times 10 inverse seconds. 2.8 times 10 is nothing but 28 at 80 degrees. So here we have a rate constant lowercase k quoted at a specific temperature. You know that vapor pressure is quoted at a specific temperature, and this rate constant lowercase k will also be quoted at a specific temperature. So how long in seconds will it take for A to decrease from its initial concentration of 0.88 molar to its final concentration of 0.14 molar? So it's a decay, right? So obviously you're going to go down in concentration. This time it's asking how long will it take to go from 0.88 to 0.14 given this rate constant for this reaction. So which equation will you use? Okay, first order with respect to K. So let's go back here. What equation can we use that's first order with respect to K? And this would be the, so I went ahead and plucked that equation out from my rate chart, plugged in the corresponding values, and I solved for T. I got 0.0656 seconds. Okay, so usually we don't take the natural log of a number with units. So we omit the units when we put it inside the natural log, and then we put the units back in. So because it decays with first order, I just put in my first order equation, and now it's just a matter of math. So this is going to decay at 0.0656 seconds from this concentration to this concentration. In other words, it's going to take 65.6 milliseconds. So pretty fast, going from taking 65.6 milliseconds to go from 0.88 to 0.14. Okay, let's look at the first order reactions a little bit more. Okay, here is our half-life for a first order reaction. Half-life is the time it takes to decrease to 1/2, and then 2 half-lives, 3 half-lives, 4 half-lives, and then 5 half-lives. All right, so first order reaction does not depend on how much you started off with. Okay, it just decays, and it decays according to natural log of 2 divided by its rate. So let's take a look at this problem here. The half-life of N2O5, its decomposition is first order. Okay, first order. So go back to your chart here. What is the half-life for a first order reaction? As we've been saying, the half-life for a first order reaction is nothing more than natural log of 2 divided by K. So we can plug that equation out and plug it in. Again, don't need to memorize anything for the exam. And that's what I did here. Okay, natural log of 2 over K, and I'm getting 1283 seconds, so 1,283 seconds. What's very interesting here is the profound nature of first order decay. It takes 1283 seconds for N2O5 to decompose to 50% of its original concentration. And that doesn't matter if I have 1,000 grams of it, 1 milligram of it, 1,000,000 grams of it, 5 nanograms of it. It doesn't matter. N2O5 is going to decay to 50% of its original value, utilizing 1283 seconds of time. So that's really amazing if you ask me about first order decay reactions or a reactant that decays with first order kinetics. Let's talk about second order, a little bit different here. The half-life for a second order reaction does depend on the initial concentration of the reactant plus the rate constant K. So let's take a look at this problem here. There's actually an error here. This should be m to the power of -1. So make sure you plug that into your note. And so the same reaction 2A going to be as seen above, but this time it's second order, having this rate constant, okay, m to the power of -1 minutes to the power of -1 at this temperature. Okay, so rate constant, lowercase k, quoted at a specific temperature. So starting at the initial concentration of this, how long will it take for it to reach a final concentration of 3.7 times 10 to the -3. So you got to remember this is a decay now, and so we're interested in how long it will take for a decay. This chapter is really on decays. We're not interested from the product perspective. We're interested from the reactant perspective, whether it's going to decay with zero order, first order, or second order. So I saw for a second order reaction, I went up to my chart and I plucked that equation out. And I plug the values in according to the equation. Okay, I modified my rate constant, and doing all of that math, I got a value of 3.17 minutes. Also, I made sure my units cancel. So if you want to calculate the half-life of the reaction, part B of this, you're going to take 1 divided by the rate constant K times the initial concentration. The initial concentration is 0.0092. So when I plugged in the half-life here, 1 over K, substituting that value for K, times AO, substituting that value for AO, initial concentration of A, I got an answer of about 2.13 minutes. All right, let's talk about zero order reactions now. So second order reactions usually have an inverse relationship to them, the decay, 1 over. First order reactions have a natural log relationship to them. And now zero order reactions really just decay. Okay, they decay over time. The half-life is right here, initial concentration divided by 2 times the rate constant. Again, you'll be given that equation for the exam. I just got to make sure you put it in right and you pick the right equation. Okay, don't pick the equation of a half-life for a zero-order reaction. Don't pick the equation for a first-order reaction. So here are the equations. These will be given to you on the exam. We're talking about it from the perspective of an individual reactant. So if we have a second reactant B, it doesn't have to have the same order of decay as A. Okay, A can be first order, and the second reactant B can be second order. In that case, the overall order of the reaction will be 3. Right? So for A going to B, that reaction, these are the pertinent equations for half-life and also how well it decays over time. All right, let's talk a little bit about activation energy and temperature dependence on rate constants. So this kind of is intuitive in my estimation. If you increase the temperature, you increase the collisions, productive collisions that molecules can undergo, and we would expect the rate constant to increase. So as the rate constant increases, the reaction rate goes faster. Temperature accelerates that because you have basically more effective collisions. Yes, you will have ineffective collisions, but if you increase the temperature to a certain extent, you will get just by statistics alone, as well as ineffective collisions, you will have effective collisions. And those effective collisions are enough to overcome the activation energy for the reaction. So increased temperature, we would expect a higher rate constant, which is a good thing if you want your reaction to proceed fast. All right, so don't forget, or do they have the right proximity? Do they have the right orientation? Are they in the right 3D geometry to actually form a product? All right, so temperature is going to increase the reaction rate, increases motion, bond rotation, rotational freedom, more degrees of freedom. Higher the temperature, we would expect higher the rate constant, lowercase k. Reaction coordinate diagram. How will a reaction proceed? Now, this is more thermodynamics here, thermodynamics in terms of energy. But we do have the Arrhenius equation, which relates the activation energy to the rate constant, lowercase k. So we do have to study this. First off, an exothermic reaction, products C and D are at a lower energy than reactants A and B. So energy is released. Okay, so how much energy is released? Probably this much energy is released. Okay. Endothermic reaction, the products C and D are at a higher energy than reactants A and B. So how much energy is required? Probably this much energy is required. And for both an endothermic and exothermic reaction, you have to get over the hump. Okay, getting over the hump is the activation energy. All right, so the hump here is a little bit larger for an endothermic reaction because it requires energy from the outside surroundings. And the activation energy is an energy, so kilojoules per mole or joules per mole, required to get over the hump, required to have enough productive collisions. All right, so somehow A and B has to get into the right proximity, geometry, and three-dimensional orientation. And once that happens, products C and D are released. All right, the Arrhenius equation is just like the Clausius-Clapeyron equation. This graph looks exactly like the vapor pressure temperature contour. And everything here is just pretty much parallels what we learned in the chapter with regards to vapor pressure and its association with temperature. Back then, if you reminisce, you increase the temperature, you increase the vapor pressure because more molecules can break free and come back down to exert a vapor pressure. Here, if you increase the temperature, you're increasing productive collisions, the rate constant will increase. So this is the exact same profile, rate constant lowercase k over temperature, and vapor pressure divided over temperature, exact same profile. And this is the three versions of the Arrhenius equation here. This is the version that equates it to a straight line, y equals mx plus b. So if you plot natural log of k, y, the y-axis, 1 over t on the x-axis, you'll get a straight line with a slope that's minus ea over r. And you get an intercept that's natural log of a. So y equals mx plus b. But you may be more familiar with this form of the Arrhenius equation, whereby you're given two rate constants and you're asked to find the rate constant of one versus the temperature at another. So here's the Clausius-Clapeyron equation, just for comparison. Here's vapor pressure at T1 versus vapor pressure at T2. Here we're having rate constant K1 at temperature T1 and rate constant K2 at temperature T2. In the Clausius-Clapeyron equation, to get over the hump is delta H vap, or the delta H of vaporization. And here, to get over the hump, it's the activation energy, EA. Okay, both of them have the gas constant R. So let's do a practice problem involving the Arrhenius equation and see if your problem answer is the same as mine. So here we have a first order constant, okay, first order, so that's something you should definitely highlight and star, put an asterisk by, so it's going to have all those first order equations, half-life and what have you. For the reaction of methyl chloride with water produces methanol and hydrochloric acid, okay, the rate constant is 3.32 times 10 to the minus 10 seconds, inverse seconds at 25 degrees. So notice we quote a rate constant K at a temperature. But that's at 25 degrees. The problem asks us to calculate the new rate constant at 40 degrees. We would expect it to be higher, increase the temperature, increase the reaction rate. So here we can just use the Clausius-Clapeyron equation, right? And this equation will be given to you on the exam. Okay, so go ahead and do this problem and see if you get the same answer as mine. So doing this problem, I'm plugging stuff in here. A couple of key points. You probably want to convert that activation energy to joules per mole to get it to cancel out with the units of R. And then the other thing is you want to convert your temperatures to Kelvin. So I converted my temperature T2 to Kelvin. I converted my temperature T1 to Kelvin. And I converted my activation energy to joules per mole. I plugged in natural log of K1 as here. As into my natural log expression. And I got everything here. All I need to do is solve for K2. So just like with the Clausius-Clapeyron equation, we have to somehow find a way to pop out K2. So first of all, what I did was I plugged all this in my calculator. Put everything in my calculator. I got a value. I got a value of minus 2.244. Okay, well that's fine. But I got all of this, my natural log and all that stuff within the natural log bracket. So how do I get rid of it? I got to take E out of both sides of the equation. So E is the inverse of the natural log. So E to the power of natural log of X pops out X. Okay, actually pops out the stuff. Okay, so E to the power of minus 2.244 was 0.1060. I popped out whatever was in my natural log, and now I can just solve for K2, and this is the answer I got. I put back the units of inverse seconds, okay, because you got to remember to put your units in, and the units for a first order reaction is inverse seconds. Also, the units for the rate constant in the problem tells us it's second to the minus 1. At 40 degrees, which is where we calculated this, our rate constant is 3.13 times 10 to the minus 9. And at 25 degrees, our rate constant was 3.32 times 10 to the minus 10. So yeah, 25 degrees, it's this rate constant. At 40 degrees, when we plugged it into the equation, it's a higher rate constant. Reaction mechanisms is the next part of this chapter. Sometimes reactions proceed by a slow step. So if that is a slow step in the reaction, we call that the elementary step. So not all reactions proceed as A goes to B directly. There's going to be intermediates. So the intermediate step, and that is the slowest step, is called the elementary step. And for the elementary step, you can actually get away with using the stoichiometric coefficient as the order of the reaction. The analogy is that if a reaction is going to go really, really fast from A to B, the slowest step in that really, really fast reaction is negligible. Catalysts actually lower the activation energy and it increases the reaction constant K. So if we look at our reaction diagram, the uncatalyzed reaction has an activation energy. The catalyzed reaction actually lowers the activation energy. So it doesn't make an endothermic reaction exothermic, nor does it make an exothermic reaction endothermic. It doesn't change the overall thermodynamic trajectory. It just takes a reaction and makes it go faster, okay, by lowering the activation energy. So there's a lot of catalysts in our body. There's a lot of catalysts that are metals, a lot of catalysts that are solids. Basically, the mechanism of a catalyst, we don't know how it does it, but somehow it lowers the activation energy and at the same time increases the rate of the reaction.